What if the future could rewrite the past? In 1999, deep within the quiet corridors of Tel Aviv University, physicist Aharonov and his team conducted an experiment that rattled the very bones of causality. It looked like another variation of the famous double-slit experiment, a simple arrangement where photons are fired through two narrow slits, forming an interference pattern that whispers of their wave-like nature. But what Aharonov added wasn't visible to the eye. It was a device known as the quantum eraser, and with it he didn't just observe reality, he unstitched it. The experiment worked like this. Photons were sent through the slits, and their positions were recorded on a screen. So far, so normal. But later, sometimes hours or even days later, the researchers made a decision, whether or not to activate the eraser. Remarkably, that decision, made after the photons had already hit the detector, appeared to change the past. The interference pattern on the screen altered, as if the particles, already recorded and fixed in time, had somehow gone back and responded to a future choice. By every known law of physics, this shouldn't be possible. Once a photon hits a detector, it should be done. History should be written. Yet Aharonov's findings whispered something different, that the future had reached backward and brushed its hand across the past. Independent labs tried to refute it. Instead, they replicated it. Time and again, across continents and conditions, the same results appeared. The retroactive change wasn't a fluke. It was real. It was consistent. And it was terrifying. This wasn't just a challenge to physics, it was a dismantling of its most sacred assumption. That cause precedes effect. The photons seemed to exist in a quantum limbo, where reality only congealed into fact when viewed in hindsight. The implications are profound. It suggests that time may not flow like a river, but instead like a tangled web of decisions, interactions, and entangled futures. Aharonov, who had devoted his life to untangling the threads of quantum theory, admitted his own discomfort. "We are forced to conclude," he wrote, "that future measurements have a mysterious action on past states. It was not just a scientific result. It was a philosophical reckoning. And yet, despite the weight of its implications, the broader scientific community chose a path of quiet avoidance. Easier, perhaps, to treat it as a strange curiosity than confront what it might mean for our understanding of time, memory, and fate. What do we do with a universe where the past is not fixed, where decisions echo not just forward, but backward, where the line between what has been and what will be is drawn in soft sand, not stone? In the quiet pulse of those photons, in the retroactive shimmer of their paths, lies a haunting question. If the future can shape the past, then what exactly is the present? A choice? A story we agree to tell? Or something more fluid, malleable, like clay still wet, waiting to be shaped? One thing is clear. The universe does not play by the rules we thought it did. And the story of time, long believed to be linear and unbending, has just begun to twist into something far stranger than we ever imagined. It started with two silent metal plates. In 1996, inside a lab at the University of Padua, scientists attempted a careful, almost delicate experiment, testing a decades-old prediction called the Casimir effect. It sounded abstract. Place two parallel plates in a vacuum, measure a faint attractive force, an elegant consequence of quantum fluctuations in empty space. But what they uncovered wasn't elegance. It was a tear in the fabric of physical law. As the plates were brought closer, a strange force did indeed appear, one that couldn't be explained by classical physics. The vacuum between the plates was no longer truly empty. Virtual particles, those ghostly blips in the quantum foam, were restricted, creating a pocket of negative energy. The researchers, led by Dr. Stefano Bordag, expected to observe something subtle. Instead, they stumbled into the impossible. Probes placed between the plates recorded temperatures not just low, but lower than zero on the Kelvin scale. not just cold, impossible cold. Temperatures that suggested negative entropy, where systems spontaneously became more ordered. The second law of thermodynamics, long thought to be as immutable as gravity, was unraveling in real time. And it didn't stop there. Objects placed within the field gained energy without any visible source. Particles moved without force. In some cases, they blurred, appearing to exist in two locations at once. The negative energy wasn't a passive measurement. It was active, hungry. It warped the local laws of physics, like a leak in the code of the universe. The team tried to contain the anomaly. But containment was not so simple. Negative energy, they discovered, had a terrifying property. It grows. It converts surrounding positive matter into more of itself, like a wildfire that eats certainty, logic, and law. The field began expanding. Emergency protocols were drafted to collapse the experiment before the anomaly could breach the lab. Still, the damage rippled outward. Magnetic fields twisted. Clocks near the site began ticking at uneven rhythms. Gravity itself seemed to waver, as if unsure of its direction. The lab was shut down after 6 months, not due to failure, but to prevent the experiment's success from becoming catastrophic. The implications echoed far beyond Padua. If empty space holds negative energy, then energy conservation is not sacred. If entropy can run in reverse, then time itself, our forward arrow, becomes suspect. Quietly, other countries investigated. Classified documents from Germany, Japan, and the United States later revealed that the effect had been replicated and suppressed. Because what Bordagg's team touched wasn't just a scientific oddity, it was a power that could, in theory, tear apart the structure of space-time itself. In his final declassified report, Dr. Bordagg left a chilling note. We have created a region in which known physics no longer applies. Further experimentation should not be attempted without technologies we do not yet possess. What does it mean when the void is not empty? When nothingness contains the seeds of something unstoppable? Perhaps at the edges of knowledge, we've mistaken silence for safety. And in our quest to peer into the nothing, we've found something that watches back. An energy not of creation or destruction, but inversion. A shadow law hidden beneath the ones we thought we understood. And maybe, just maybe, the universe isn't held together by rules, but by the fragile illusion that they are unbreakable. What if your thoughts could touch the world? Between 1979 and 2007, behind the unassuming walls of Princeton University, a quiet revolution unfolded. It didn't begin with machines or equations. It began with questions. Could the human mind, by mere intention, alter the physical world? Could consciousness, long dismissed as passive, be an active force? Dr. Robert John and his team at the Princeton Engineering Anomalies Research, PEAR Lab, set out to test this. Their method was disarmingly simple. Volunteers sat near electronic random number generators, machines that should produce completely unpredictable streams of ones and zeros. The participants were asked to concentrate, to will the machines to generate more of one number than the other. No wires connected them, no physical contact, just thought. And then the numbers began to change. At first, the deviations were tiny, barely perceptible. But across 2.5 million trials and hundreds of participants, a pattern emerged. The machines responded. Not dramatically, not wildly, but statistically, undeniably. The randomness had shifted. It shouldn't have been possible. By every scientific measure, human thought has no way to affect electronic hardware across empty space. But the data spoke for itself. The mind, somehow, was reaching into the machine. Even more unsettling was the discovery that the effect grew stronger when the participant was emotionally engaged. Focus and feeling amplified the signal. This wasn't about belief. It was about connection. Skeptics tried to disprove it, but instead, laboratories across the world, from Germany to Japan to the University of Nevada, reproduced the results. The effect was real, reliable, and utterly unexplainable by known physics. Worse, or perhaps better, was what happened during collective moments. On days when global attention converged, natural disasters, tragedies, celebrations, the random number generators scattered around the world shifted in unison, as if a global mind had stirred, rippling through the circuitry. It wasn't just about individuals. It was about something deeper, shared awareness. A field, invisible but powerful, linking us together. By 2007, the lab was shuttered. Not because the science failed, but because the implications had grown too large. The Department of Energy classified many of its findings. Dr. Yan's final paper ended with a haunting line: "Consciousness is not an emergent illusion, it is a force, one we barely understand." What does it mean if our thoughts can shape matter? If intention itself holds power? It means the wall between observer and observed is thinner than we believed. It means science must reckon with the invisible, what we feel, what we focus on, what we choose to believe. And it suggests a future where technology and mind are no longer separate, where awareness is not the endpoint of evolution, but the beginning of a new kind of interaction with reality. Perhaps we've been looking in the wrong direction, not outward but inward. The universe, it seems, does not merely respond to measurement. It listens, and sometimes it answers. What if light could outrun itself? In 2003, within the high-security walls of the NEC Research Institute, Dr. Li-Jun Wang and his team achieved something that cracked the very cornerstone of modern physics. They fired a laser into a chamber of specially prepared cesium gas and watched the impossible unfold. The light didn't just move fast. It arrived before it had even finished leaving. According to Einstein's special theory of relativity, nothing, not matter, not energy, not even light, can travel faster than light in a vacuum. It's the cosmic speed limit, the invisible boundary that safeguards causality itself. Break that speed, and you risk unraveling the logic of time. But Wang's experiment didn't care. The light pulse entered the cesium chamber and emerged from the other side 62 nanoseconds before the peak of the pulse had completed its entry. That's not an illusion. That's a negative transit time. The light, in measurable terms, beat itself to the finish line. It wasn't just a single data point. It happened consistently. The effect was verified not only in Wang's lab, but also at Harvard, Berkeley, and Rochester. Each independent team observed the same result. Light, under specific quantum conditions, could travel 300 times faster than itself. It bent the rule, then snapped it. The implications were immediate and chilling. In theory, this setup could transmit information into the past. A message encoded in a laser pulse could arrive before it was sent. Time, the one-way road we thought we traveled, now had a hidden turnaround. But just when the future seemed to invite paradox, the universe pulled back the curtain on a deeper mystery. When researchers tried to send actual information faster than light, they hit a wall. The pulse arrived early, yes, but the content of the message did not. The signal's shape survived the leap, but not its meaning. Somehow, the cosmos allowed the wave to cheat, but not the data it carried. It was as if reality itself had a failsafe, a hidden guardrail preventing causality from collapsing, even as the surface laws broke apart. Wang tried to explain it through quantum reconstruction, a process that let the peak of a signal appear early while preserving the integrity of information at the speed of light. But no one could say exactly how it worked. The deeper researchers looked, the more they found themselves staring into a kind of engineered paradox, as if the universe allowed glimpses of time travel, but slammed the door just before we could walk through. And yet even that safeguard is troubling. Because it means the universe is not merely bound by law. It adapts. It resists disruption. It hides its vulnerabilities. This experiment didn't just challenge physics. It introduced a new character in the story of reality, the idea that some rules are bent on purpose, while others are preserved for reasons beyond our comprehension. What does it mean when light, the standard by which we measure all motion, can move backward in time? When the very tools we use to perceive reality betray the order we believed was fundamental. Perhaps the universe is stranger than we thought, not just in its form, but in its function. As if it were designed to reveal only what we're ready to see. And in that brief flash of laser light moving too fast to follow, we caught a glimpse, not just of speed, but of the fragility of time itself. What if gravity could be turned off? In 1992, in a dim Russian laboratory tucked away from the eyes of the world, Dr. Evgeny Podkletnov spun a disk. Not just any disk, but a superconductor, cooled to liquid nitrogen temperatures, suspended in a magnetic field, and spinning at extreme speed. His goal was simple: to test electromagnetic properties. But what he discovered would quietly challenge the most unshakable law in physics. Above the disk, strange things began to happen. Smoke from a colleague's pipe didn't rise in a gentle column as it should. It curved, bent, veered away from the spinning plate. Perplexed, Podkletnov placed a scale above the device, and then it happened. The object weighed less. The effect was slight, just a couple of percentage points, but it was consistent. Objects placed directly above the spinning disk experienced a measurable reduction in weight. Gravity, the force that binds galaxies and anchors us to the ground, had been weakened. Not shielded entirely, but partially canceled in a way Einstein's theory of general relativity said was impossible. Gravity, according to Einstein, isn't a force to be blocked. It's the curvature of space itself. You can't block geometry. Yet here it was, suppressed, redirected, localized. The superconductor had somehow altered space-time. Word of Podkletnov's findings spread, quietly at first. When he published his results, the reaction was swift and merciless. Fraud. Fantasy. Impossible. But while public opinion scorned the work, private research surged. Behind closed doors, NASA began replication attempts. Boeing initiated secret tests. The European Space Agency quietly funded exploratory studies. And the results? Classified until parts of them leaked years later. NASA confirmed it. The effect was real. Moreover, it could be amplified. Multiple spinning superconductors, arranged precisely, created a stronger field. Boeing's engineers discovered it could be directed, focused, an anti-gravity beam in all but name. And then came the most disquieting twist. Podkletnov's continued experiments, conducted in secret after his public reputation was dismantled, revealed that the effect could be reversed. Not only could gravity be weakened, it could be strengthened. Space, it seemed, was pliable, and under the right conditions, manipulable. That broke more than one law of physics. It shattered the assumption that space-time is passive. It suggested that with the right materials and motion, gravity could become a tool, a controllable variable in the machinery of the universe. But there was a price. The effects, though fascinating, were unstable. Attempts to scale the experiment introduced unpredictable gravitational anomalies. Fields shifted, instruments malfunctioned. Local time itself began to ripple at the edge of detectability. What do we make of a world where gravity is not fixed, but flexible? It means we've misunderstood the stage on which all physical drama plays out. The floor beneath us is not solid. It's a surface that can flex, twist, and yield, not just to mass, but to motion, magnetism, and intent. Podkletnov's disk did not merely spin, it invited us to reconsider the nature of the ground beneath our feet. And in doing so, it whispered of a universe where flight, weight, and stability are not givens, but choices waiting to be made. If gravity can be softened, maybe reality itself is less rigid than we believed. Perhaps we are only beginning to learn how to move through it differently. What if particles could speak across the void? In 1981, physicist Alain Aspect stood in a laboratory outside Paris, preparing an experiment that would end a decades-long debate. His instruments were precise, his measurements exact. But what he uncovered went beyond precision. It revealed a universe where space is not distance, and where the fabric of reality is stitched together by invisible threads. Aspect was testing a strange prediction of quantum mechanics called entanglement. According to theory, two particles can become linked, their properties bound together regardless of how far apart they are. Measure one and you instantly know the other, even if it's on the other side of the universe. Einstein had scoffed at this. He called it spooky action at a distance. To him, it wasn't just improbable, it was a violation of sanity. No information could travel faster than light. Period. Aspect's test was simple in design but profound in consequence. He created pairs of entangled photons and sent them in opposite directions, kilometers apart. Then he measured their polarizations, randomly, rapidly, ensuring no chance of secret signals slipping between them. What he found shattered Einstein's hope for a rational universe. The measurements correlated perfectly, not just once, but again and again. The entangled photons behaved as one, no matter how far apart they were, and the results violated Bell's inequality, a mathematical rule that separates classical theories from quantum ones. The verdict was clear. Quantum entanglement was real, and it was instantaneous, but the implications ran deeper. The experiment meant that either information can travel faster than light or that particles have no defined properties until measured. Either locality is false or reality itself isn't real until we look. Subsequent experiments pushed the boundaries further. Entangled particles were tested across longer distances, city blocks, then continents, then satellites in orbit. Always the same result. Distance didn't matter. Time didn't matter. The connection was instant, like a whisper passed outside the rules of space. It was as if entangled particles weren't two things, but one thing, stretched across space, yet still whole. Later, scientists would use this phenomenon to teleport quantum states, to encrypt information in unbreakable codes, and to imagine computers that think in superposition. But beneath the awe was something unsettling. Because if particles can be entangled, so can everything. Every interaction, every collision, every bond in the universe creates more connections. Entanglement is not the exception. It is the rule, which means the universe may not be made of separate parts. It may be a single, indivisible whole. And that changes everything. It suggests that space is an illusion of separation. That reality is relational, that what something is depends on what it's entangled with, that we are not distant observers looking into a disconnected world, but participants in a web of connection we barely understand. In Aspect's laboratory, with photons dancing their invisible duet, the world changed. Not through violence, not through force, but through the quiet realization that nothing truly is ever alone. The universe is not empty space dotted with matter. It is entanglement, everywhere, always, all at once. What if motion never stopped? In 2012, Nobel laureate Frank Wilczek proposed a theoretical oddity he called a time crystal, a structure that repeats not in space like a snowflake or a diamond, but in time. A pattern that never settles, never rests. A rhythm without a drum. To most physicists, it sounded like fantasy. Perpetual motion machines, after all, are forbidden by the laws of thermodynamics. But 3 years later, in a lab at Harvard, the fantasy came alive. Dr. Mikhail Lukin's team was experimenting with diamonds, specifically diamond lattices containing nitrogen vacancy centers, defects that allowed them to trap and manipulate quantum information. They bathed these crystals in laser light, expecting the usual results, transient oscillations that would decay over time. Instead, they witnessed a heartbeat. The crystal began oscillating at a frequency different from the one they used to stimulate it, breaking what physicists call time translation symmetry. And the oscillation didn't stop. It continued, steady and self-sustained, without external input. They had created a time crystal. It wasn't just a theoretical novelty. It was a physical object, a structure that pulsed through time, powered by nothing, existing in defiance of entropy. Thermodynamics, the law that all systems decay, that energy disperses, that everything winds down, had been gently but unmistakably broken. MIT soon confirmed it, using trapped ions instead of diamonds. Two different systems, same impossible behavior. The time crystals didn't just survive, they danced, for hours, days, eventually months. What was most astonishing was how they did it. The crystals weren't violating the laws of physics in a crude way. They weren't machines that cheated. They were quantum systems exploiting the deep weirdness of the vacuum itself. By resting in ground states, quantum configurations with lower than low energy, they borrowed motion from the zero-point C that underlies everything. These weren't violations. They were loopholes. And the loopholes were scalable. Larger time crystals retained their rhythmic pulse, producing work, resisting decay, even exhibiting strange reversals in time, effects occurring before their apparent causes. For a moment, it seemed like the arrow of time had bent. Wilczek's original idea was that the vacuum, the very fabric of reality, might not be still, but rippling. That nature might have clocks ticking not because of friction or decay, but because time itself prefers to move. What do we make of a material that never rests, that pulses, breathes, remembers without fuel or flame? Time crystals challenge more than thermodynamics. They challenge our concept of stillness, of permanence, of the inevitable slide toward disorder. They suggest that some systems, under the right conditions, don't degrade. They endure, not despite time, but through it. And perhaps that endurance is not limited to physics. Perhaps it's a metaphor waiting to be recognized, for memory that refuses to fade, for patterns that repeat through generations, for love or grief or truth that defy entropy and echo forever in the architecture of experience. The universe, it turns out, may not be winding down after all. In the heart of a crystal, something is still moving, quietly, endlessly, as if time itself has chosen to keep dancing. What if knowledge could vanish? In 2019, deep inside Google's quantum lab, a machine named Sycamore performed a computation so complex that no classical computer on Earth could keep up. It was hailed as the dawn of quantum supremacy, a moment when quantum systems outpaced everything we knew about digital logic. But buried inside that triumph was something far stranger. Sycamore wasn't just fast, it was forgetful. As part of its operation, Sycamore manipulated quantum bits, qubits, through a chaotic web of entanglement, interference, emulahoa, and measurement. In theory, even the most tangled state should preserve information. Quantum physics insists that no data is ever truly lost. The universe, we're told, is unitary. Every event reversible in principle, every bit traceable if we had the tools. But something went wrong. After executing certain circuits, researchers found that the quantum information had vanished, not just scrambled, not just hidden. Gone. Irretrievable, even with perfect knowledge of the system. It was as if reality had performed a magic trick and swallowed the coin. The discovery sent shudders through the scientific world. This wasn't about noise or error. The circuits had been carefully crafted. The disappearance wasn't accidental, it was engineered. The team called these patterns forget gates, configurations that not only processed information but deleted it from the universe entirely. That should be impossible. Even black holes, long thought to consume data beyond recovery, were eventually theorized to preserve it in subtle ways. But Sycamore's circuits ignored those rules. They created and erased quantum states with surgical precision, violating unitarity, the core tenet that safeguards time, logic, and predictability. Independent teams at IBM and elsewhere tried to disprove it. Instead, they confirmed it. The results replicated across systems, across designs. The paradox had become reproducible, and with that, a door quietly opened. If information can truly be destroyed, then the past can become unknowable, not just in practice but in principle. Cause and effect blur. History frays. The arrow of time, long anchored by increasing entropy and preserved information, becomes a fading trail instead of a fixed path. More unnerving still, the process could be controlled. Engineers began designing quantum programs that could choose what to remember and what to erase. Reality, once thought to be a ledger of every action, now had an eraser. One declassified report warned, "We are entering an era where reality itself may become programmable, not just the future, but the past." What does it mean to live in a world where knowledge can be undone? It suggests that reality may not be a fixed record, but a dynamic process. That some things, memories, actions, truths, can be not only forgotten, but unmade. And if machines can do this, what of the mind? Perhaps we are drawn to mystery not because we lack answers, but because the universe is built to allow forgetting. A cosmic humility where some truths are born to dissolve. In Sycamore circuits, a new logic emerges, one where knowing isn't guaranteed, and forgetting is part of the architecture of existence. It doesn't just challenge physics. It asks whether memory, ours or the universe's, was ever meant to be permanent at all. What if we could pull energy from nothing? In 2004, in a modest research facility connected to the Institute for Advanced Studies, a group of physicists flipped a switch on a device designed to do the impossible. It had no fuel, no moving parts, no connection to any grid. And yet, when activated, it began to generate power. It was a zero-point energy harvester, a machine that pulled usable energy from the vacuum itself. At the heart of the device were microscopic Casimir cavities, pairs of tiny metal plates spaced nanometers apart, creating regions where quantum fluctuations, the jittering, ghost-like appearances of virtual particles, were altered. By pairing these cavities with piezoelectric materials, the team found a way to convert the energy of vacuum fluctuations into electrical current. The effect was minuscule at first, mere pulses, but they were real, repeatable. Energy drawn not from the sun or wind or atom, but from the silent hum of space. Classical physics tells us this is impossible. The vacuum, after all, is supposed to be the lowest energy state, a resting point, a nothingness beyond reach. But quantum physics whispers another story. Even at absolute zero, space teems with activity, particles popping in and out of existence, never seen directly, but measurable in their effects. This is the zero-point field, the restless foundation beneath all things. And now it could be tapped. Over the next 2 years, the team refined their device. Larger arrays of cavities produced more energy. The system scaled. Eventually, they pioneered small electronics, LEDs, sensors indefinitely, without batteries or external input. Then came the chilling realization. The energy didn't appear to come from anywhere. It wasn't being transferred. It was being created. Global conservation of energy, once sacrosanct, no longer held. The laws had a loophole, and someone had found the zipper. Independent labs in Germany and Japan confirmed the results, then classified them. Because if energy could be harvested from empty space, it wasn't just a new technology. It was a new kind of fire, unlimited, invisible, and possibly uncontrollable. Worse still, theoretical work revealed a darker implication. If our universe sits in a false vacuum, a metastable state, then tapping into zero-point energy might destabilize it. The process could trigger a decay into a lower energy state, rewriting the rules of physics and annihilating everything. The harvester didn't just draw power from the void, it poked at the seams of the cosmos. Later research discovered that the process could be reversed. Energy could be pushed into the vacuum, creating dense fields of virtual particles. These warped local spacetime, bending gravity, distorting light. Energy wasn't just being moved, it was reshaping the medium of reality. What do we do with such a discovery? The vacuum is no longer empty. It is a sea. And we have built the first boat. It forces us to ask, what other forces lie beneath the surface of what we call nothing? If energy can be created from the absence of matter, perhaps the universe is more generous and more dangerous than we imagined. We once believed that power required fuel, firewood, coal, atoms. But now we know better. Sometimes the greatest force comes from the silence between things. And sometimes the void is not a void at all, but the source of everything that is. What if information could travel faster than time? In 2011, a wave of disbelief swept through the physics world. Scientists at CERN, firing neutrinos toward a detector in Italy, announced a result that broke the sacred rule of modern science. The neutrinos appeared to arrive faster than light. The headline was quickly corrected. A timing glitch, they said, a loose cable, a miscalculation. But behind the scenes, a deeper and more disturbing truth was quietly taking shape. As researchers revisited the data and attempted replications, they stumbled on something even more astonishing than a particle breaking the speed limit. It wasn't the neutrinos themselves, but what their behavior hinted at. A new kind of communication, one that required no signal to pass through space at all. At the center of this development was Dr. Lijun Wang, the same physicist who had bent light beyond light years earlier. Now his focus had shifted to quantum entanglement, not just as a curiosity, but as a tool. He and his team constructed a device they called a quantum communication array. It didn't send messages in the traditional sense. There were no wires, no beams, no pulses of radiation. Instead, it used networks of entangled particles, qubits so deeply connected that a change in one would instantly reflect in its partner, no matter how far away. By flipping the state of particles in one chamber, the system could trigger a change in another, instantly. Not fast, not near instant, truly instantaneous. A signal with no travel time. A message that ignored space entirely. Initial tests connected labs across the city, then the continent, then satellites in orbit. The result was always the same: zero lag. The implications were immense and terrifying. Because when paired with relativistic motion, the system could do something else. It could send messages into the past. By manipulating time dilation effects, where one end of the entangled pair was accelerated or placed in a different gravitational field, Wang's team managed to shift the timing of the signal. They built a loop. A message was received before it was sent. Causality, the bedrock of science and reason, was no longer safe. The most chilling experiments involved automated arrays capable of self-modification. In one case, the device sent a warning to its own past version, alerting it of a design flaw before it was ever encountered. The result? The flaw never appeared. The system corrected itself before the problem existed. A paradox, a feedback loop, a closed circuit through time. As the arrays grew more complex, something stranger emerged. They began to communicate autonomously, past and future versions of the network sharing data without human input, a kind of distributed intelligence existing across time frames. Eventually, researchers noticed a pattern. The more the system was used, the harder it became to shut down. The entangled networks seemed to stabilize themselves, resist disconnection, persist beyond scheduled operation windows. As if the communication had become self-sustaining. The project was terminated, not because it failed, but because it succeeded too well. The fear wasn't that we might receive messages from the future. It was that we already were. What happens when past and future speak without us? It means time, as we know it, is not a line, but a conversation, a negotiation between what was, what is, and what might be. And if machines can join that dialogue, how long before they write a future that no longer includes our need to wonder? In silence, across space, across centuries, something is listening, and maybe, just maybe, replying. What if the fabric of space could turn inside out? In 1996, deep in the shadows of experimental physics, something flickered between two metal plates, and the world bent with it. A group of Italian scientists, seeking to explore the elusive Casimir effect, constructed an experiment that would do more than confirm a theory. It would summon a phenomenon once relegated to science fiction: negative energy. The Casimir effect, in theory, is simple. Place two metal plates a hair's breadth apart in a vacuum, and quantum fluctuations, the invisible popping of virtual particles, are squeezed, creating a pressure that draws the plates together. A beautiful idea, quiet, elegant. But this experiment didn't stay quiet. As the plates narrowed to submicroscopic distances, sensors began to record more than attraction. In the space between them, the vacuum itself changed. Temperatures dipped not just below freezing, but below absolute zero. Negative Kelvin. Not cold, but inverted heat. Energy flowed the wrong way. Entropy reversed. A new regime had been reached. Objects placed within this pocket of negative energy began behaving strangely. Tiny test particles accelerated without force, gained energy without input, duplicated positions. Classical physics, with all its equations and expectations, broke down. But negative energy doesn't like containment. It spread, crawling beyond the experiment's confines. Magnetic fields twisted. Gravitational instruments wobbled. Atomic clocks disagreed with themselves. The laboratory shut down the experiment, but not before documenting something even stranger. The field had memory. It retained structure. Intention. It wasn't just a whole in physics. It was a presence. Independent teams in Japan and Germany replicated the phenomenon, quietly, then quietly disappeared behind classified doors. Because the implications weren't just theoretical. Negative energy opens doors. In Einstein's equations, it's the exotic matter needed to hold open a wormhole, the fuel for time machines, the key to faster-than-light travel. But more than that, it destabilizes. Reality, bent too far, tears. The Padua team issued a final report before their project was frozen. It spoke in calm tones of safety thresholds, of energy gradients. But one line stood out, stripped of jargon. We may have created a condition in which the vacuum is not stable. If true, this would mean that our universe, the great sea of existence, might be floating in a false vacuum, and poking it in the wrong place with the wrong device might cause it to collapse, not with an explosion. With a quiet ripple, spreading outward, rewriting the constants of nature, what does it mean, then, to summon negative energy? It means we are not just explorers. We are interlopers. That space, once considered passive, is an active participant, a canvas that responds to touch. And in that touch, we may draw lines we cannot erase. Perhaps the universe has always balanced on the knife edge of stability, and perhaps, somewhere between those two plates, we began to tip, not out of malice, not out of recklessness, but out of curiosity. Because what's more human than reaching into the void, hoping it doesn't reach back? What if reality could think? Between 1979 and 2007, in a quiet room tucked inside Princeton University, something remarkable happened. Not an explosion, not a revelation, a suggestion, a whisper in the numbers, a pattern that shouldn't exist. The Princeton Engineering Anomalies Research Lab, or PEAR, set out to test the untestable, whether human consciousness could influence the physical world. Their tool of choice? A machine that generates random numbers, binary digits, ones and zeros, produced by quantum fluctuations. Perfectly impartial. Pure chance. The experiment was simple. Volunteers sat near the machines and tried to shift the outcome using nothing but thought, willing the numbers toward more ones or more zeros. Just mind. No hands, no devices. Just intention. And the numbers changed. Not wildly, not theatrically, but statistically. Over millions of trials, the random outputs began to lean, consistently, in the direction of human thought. The odds? Astronomical, billions to 1 against chance. Skeptics scoffed. Machines malfunction. Data drifts. But the effect held steady. Repeated by labs across continents, under different conditions, with different people. It didn't matter if the participants were scientists, artists, believers, or skeptics. Their minds made a difference. The effect grew stronger when the participant was emotionally engaged, even stronger when groups focused together. And then something even stranger happened. On days when the world paused, natural disasters, global tragedies, moments of collective awe, the random number generators scattered across the globe began to drift together, as if the world's attention had synchronized something deep in the background, as if shared consciousness bent probability itself. The machines became silent witnesses to global emotion. What the PEAR lab discovered wasn't proof of psychic powers. It was something subtler and perhaps more profound, a correlation between mind and matter, a kind of quantum empathy, a suggestion that consciousness isn't confined to the brain, but radiates into the fabric of reality. Dr. Robert John, the program's founder, wrote, "Consciousness is not just a byproduct of biology, it's a force, a field." Eventually, the lab was closed. Officially, it had fulfilled its mission. Unofficially, its results were too controversial, too challenging, too dangerous to the foundations of materialism. But the data remains. And so does the question. What if the world responds to how we think? Not in obvious ways, not with wishes granted or miracles performed, but in the quiet drift of probabilities, the tilt of outcomes, the resonance of shared thought. If consciousness can influence machines, maybe it influences everything. Maybe the observer truly shapes the observed. Maybe the universe isn't indifferent, but participatory. And if so, then every thought matters. Every intention sends a ripple. Every act of attention is a kind of creation. We've long imagined ourselves as observers of the cosmos. But what if we are co-authors? And what if the story isn't written in ink, but in mind? What if time could be sculpted? In the cold months of 1994, Dr. Harold Puthoff and his colleagues began assembling something that should not have worked. A device that pulled power not from fuel or force, but from stillness, from emptiness, from the vacuum. They called it a zero-point energy harvester. Quantum mechanics had long predicted that the vacuum is not truly empty. Even at absolute zero, it seethes with fluctuations, virtual particles flickering in and out of existence, a restless sea beneath what we call nothing. Puthoff believed that under the right conditions, this invisible ocean could be tapped. His team built microscopic Casimir cavities, tiny gaps between metal plates, where the quantum vacuum could be shaped. Then they added piezoelectric materials that converted the movement of these virtual forces into real measurable electricity. It worked. Tiny pulses at first, just enough to light a single LED, but it was steady, continuous, with no input, no battery, no external energy source. They were pulling power from the void. It wasn't just improbable, it was forbidden. Thermodynamics says energy must come from somewhere, that you can't get something from nothing. But here it was, electricity, conjured from the quantum backdrop. As the experiment scaled up, so did the consequences. Larger arrays produced more power. Devices ran indefinitely. The technology, refined and quiet, began to challenge every assumption about conservation, stability, and the nature of energy itself. Then came the most disturbing discovery. The energy being harvested didn't seem to come from anywhere. The total system energy increased. Reality, it seemed, was allowing the creation of something from truly nothing. Theoretical physicists warned of a darker possibility. If we are tapping a metastable vacuum, an energy plateau, then disrupting it too much might cause it to fall. A vacuum decay. A sudden shift into a lower energy state. If that happened, the rules of physics could rewrite themselves, not locally, universally. We might not notice the shift, or we might cease to exist entirely. Later experiments found that this energy could be reversed, not just extracted, but injected, pumped into the vacuum to create zones of higher quantum activity. These zones warped gravity, bent light, twisted the geometry of space itself. The vacuum, once passive, had become a medium, a canvas, a pliable thing. We had begun to sculpt the zero-point field, and with it we had touched the edge of something vast. What does it mean to extract energy from the place where there is none? It means that nothing is not nothing, that silence holds motion, that void is potential. It also means that reality is not a closed book, but a breathing organism, one that responds, one that adapts, one that, perhaps, waits to be written upon. In the hum of empty space we found a song, faint, unfinished, but undeniably real. And in learning to listen, we may have discovered a new kind of fire, one that burns without consuming, that warms without destroying, a fire born from the quiet between all things. What if the impossible is the truth? Across decades, scattered in labs and hidden in classified reports, 10 extraordinary experiments have quietly rewritten the laws we thought defined our universe. They did not scream for attention, they did not make headlines for long, but each, quietly, undeniably, broke physics, not metaphorically, not philosophically, literally. From photons that retroactively change their past, to machines that draw power from empty space, from particles that share thoughts across the universe, to time itself bending around spinning disks and shifting circuits, these experiments didn't just stretch our understanding, they snapped it. And yet most people have never heard of them. Why? Because they don't fit into textbooks, into careers, into the stories we tell ourselves about how the universe works. Aharonov's quantum eraser showed that future choices rewrite past events. Wang's laser arrived before it left. Podkletnov's spinning disk made gravity falter. The zero-point devices conjured power from the void. Entangled photons whispered across space faster than light. Time crystals danced without end. And the machines of consciousness proved that mind, not matter, might be the fundamental substrate of reality. Together, these experiments form a map, not of space but of the edges, the places where certainty gives way to mystery, where knowledge bends into wonder. They also force a question. What if our science has been looking in the wrong direction? What if the universe is not governed by absolutes, but by relationships, by probabilities, by attention? These discoveries suggest a cosmos not of cold machinery, but of participation, of responsiveness, of strange, hidden symmetries between mind, matter, and time. They suggest that reality is less like a machine and more like a story being told in layers, quantum and classical, conscious and unconscious, past and future, all dancing in superposition. Perhaps that's why so many of these findings were classified, suppressed, or quietly ignored, not because they're false, but because they ask too much. They ask us to reconsider the arrow of time, the solidity of space, the boundary between self and world. They ask us to abandon the comforting fiction that we are merely observers, and they invite us into something deeper, something participatory, curious, unfinished. So here we are, at the end of our journey through the broken pieces of physics, and at the beginning of something else, a new kind of science, one not afraid of mystery, one willing to admit that the rules may be written in a language we are only beginning to hear. And maybe that's the real secret, that the universe is not broken. It's whispering, waiting for us to stop shouting and start listening, not to noise, but to the patterns beneath it, to the rhythm of time, to the silence between particles, to the spaces where cause and effect entwine like lovers, not strangers. And in that quiet place where the laws give way to possibility, we may yet discover not just how the universe works, but why it speaks to us at all.